Hi folks, welcome to the Thursday live session. We're going to do some problems from 6.6. If there's time, I might stop the video and do a separate video for some of the problems in 8.1, or at least just an introduction to functions of multiple variables. So let me switch over to the whiteboard and we'll get started. So section 6.6 has to do with the area between two curves. And it's one of these sections, we've maybe had some other sections like this, where the new calculus is actually not that hard, but the new algebra might be challenging. I have a problem I want to do in a moment, but first, just to make sure that we're really clear here, talk about the area between two curves. By convention, I'm just going to say that the taller one with the greater y value, I'll just label that f of x. So f of x is some curve. We have a second curve, g of x. And we want to find the area between these two curves for some range of x values. Now for this general example, I'm going to let the left-hand endpoint actually be where the two curves intersect. I'll call that A, and then we'll go until we get to B. Okay, so just to shade what we're looking for here, I'm going to calculate or talk generally about the area between two curves like that. Okay, so really this section just has to do with properties of geometry more so than calculus. If we want to find the area between two curves, what we're going to do is find the area beneath the taller curve, so beneath f of x, and then we're going to subtract the area beneath g of x, and what will be left over is this area in between. So really it's just a geometric reasoning problem where we're going to do two integrals. We're going to do a single integral that has a difference involved in it. And so here's the integral that we'd set up to do that. So that area of that region there, let's call that R, why not? So the area of that region is going to be the definite integral from A to B of the taller function, so f of x minus g of x dx. And if we want to, just using properties of definite integrals, we could evaluate these as two different definite integrals, or we could do that subtraction first and then evaluate the integral. So here's a second way that we could write that. Integral from a to b of f of x dx minus the integral from a to b of g of x dx. I'm not saying we want to do one or the other, it's just two different ways to calculate the same thing. So one thing we could think about, if we go back to Riemann sums, really what we're doing, we're still doing approximations. If we have a finite number of rectangles, we're just fitting rectangles in between the curve, and the definite integral allows us to do an infinite number of those rectangles. So in WebAssign, there's a variety of problems, some of which they give you A and B, or it's really, you can read off of a graph what the lower x value is and what the upper x value is for integration. When you do that, it's really easy. You just put those values into the definite integral for the lower and the upper endpoint here. There are other problems where you might need to use some algebra to figure out what the lower and upper endpoints are. So I want to show some problems involving that. Let me hop over to WebAssign real quick, and we'll look at some of the problems that they have there. I think, here we go. Okay. So the earlier problems in 6.6, you're able to see on the graph what the endpoints of integration are. So for example, in problem 1, we can see that shaded region begins at x equals 0 and goes to x equals 2. So those would be our endpoints of integration. In problem 2, this is kind of what I want to talk about here. Problem 2, we actually have to solve for the upper endpoint. We can see that it looks like it's around 4, but we want to verify that that's correct. We'll go down and look at some other ones here later in this session. There's some more complicated area problems, like problem 10 is a little bit challenging. It involves 3 curves. We'll take a look at that one in a minute. We'll go back to the whiteboard here. Okay, so what I want to do as an example here is find the area between these two curves. So y equals x minus 1 and y equals negative x squared plus 2x plus 1. Now you're not supposed to know exactly what these look like, but you can probably figure out the second curve is a downward opening parabola. The upper one is a line of slope 1. We don't have to be able to graph it in order to find the area between the curves. So what we want to do is we want to find the points at which these two curves intersect. That is, that they have the same x and y values. And so what we can do is set these two equations equal to each other. Say the y value from the line will equal the y value from the parabola. So if I set this up, so x minus 1 equals negative x squared plus 2x plus 1. Well, this is a quadratic equation, right? I can solve that using factoring or graphing or the quadratic formula. So for quadratic, I want to get all the terms on one side, so I'll add x squared to both sides. I'll subtract 2x, so that would give me negative 1x over here, and then I would subtract 1 as well. So here's my quadratic just with x squared added to both sides, 2x subtracted from both sides, and 1 subtracted from both sides. As it turns out, this one factors. So it factors into x minus 2 times x plus 1. And so that tells us that x equals 2 and x equals negative 1. Oops. Those are the solutions to this equation. And remember what the equation was. The equation was looking for points on the line and the parabola that have the same x and y values. So what that tells us then is our integral is going to go from negative 1 to 2. Now, since we don't have a graph for this one, it might be challenging to figure out which one's the taller function, which one I'm going to call f of x, and which one I'm going to call g of x. One thing that you can do is you can pick a test value and just plug it into your two functions. So if we're going from negative 1 to 2, they're both continuous functions, so they're not going to jump around or have asymptotes or anything like that. So if I plug in like 0, for example, my line would have y value negative 1, and my parabola would have y value positive 1. So that tells me that my parabola is the upper function here. And so what I'll set up then is the equation for the parabola. So negative x squared minus 2x plus 1, right? That's our f of x minus the equation for the line. So minus x minus 1 all times dx. Move this over a little bit, get rid of that. One common mistake I see when we're subtracting functions is people might not put that second function in parentheses and only subtract part of it instead of the whole thing. This whole thing's times dx. So let me finish this problem here. So I can simplify that before I evaluate the integral. So we're from negative 1 to 2. And let's see, if I completed the subtraction, I'd have negative x squared minus 2x minus x. See, did I do that right? Oh, sorry, that's supposed to be a plus 2x. There we go. So plus 2x and plus 1. So 2x minus x gives me plus x. And then I have a, what do I have here? I have a 1. And then I'm subtracting negative 1, so I have plus 2. And so I can take those antiderivatives. Negative x squared will go to negative x cubed over 3. X will go to x squared over 2. And 2 will go to 2x. And we'll evaluate those at the endpoints 2 and negative 1. So a little bit of space here. Let's come up here to finish the problem. So if I plug in 2, I would have negative 8 thirds as my first term, right? Because 2 cubed is 8, plus 2 squared over 2, so that would be 4 divided by 2, so plus 2, plus 2 times x, so plus 4. So again, this is that antiderivative with 2 plugged in, and then we're going to subtract the antiderivative with negative 1 plugged in. So we plug in negative 1, a negative number cubed is negative, and then we have a negative sign there, so that would be positive. By far, I think just sign errors, that's the most common mistake that people have on these problems. So first term would be a positive 1/3, right? Because we make it negative after cubing it. And then we have -1 squared over 2, so it's positive 1/2, and then plus 2 times -1, so -2. And I'm not going to finish the problem here. I don't think we want to spend too much time on fractions, but really the key steps here are setting up the right integral, so having the right function on top and on the bottom, and having the correct endpoints of integration. The problems in WebAssign vary a little bit in difficulty. We'll try and go back there for a moment. Yeah, maybe I'll give some commentary on these WebAssign problems. We're not going to solve all of them because they're a pretty significant part of your grade. So for example, problem 7 here, we have the function y equals the cube root of x, and then the other function is y equals 1 over x. And a nice thing that they've done here is they've actually labeled the intersection point 1, 1. But if we didn't have that, we could set 1 over x equal to the cube root of x, cube both sides, and you'd end up with the equation that x equals 1. And our upper end point is 27 here. So for this problem, we'd set up the integral from 1 to 27, right? Those endpoints of integration are always x values. And our integral would be cube root of x, because that's the upper function, minus 1 over x. So some problems ask you to find the area of the shaded region. One thing to remember in this section is the definite integral counts up signed area, so positive area and negative area. We know in reality there's no such thing as negative area. So for a problem like number 9, what we want to do is break this into 2 integrals. So take one integral from 0 to positive 2, and then take another integral from -2 to 0, knowing that it will count that area as negative. So what we can do then is put this together in 2 pieces. There are some other problems like this, like question 10, for example. We have to break it up into 2 integrals. If you can see, boy, that hover text is really annoying. The region that we're looking for here, if we think about it in 2 pieces, to the left of the y-axis is a triangle. That area we could find as the integral of the line y equals x plus 6 minus the line -1/2 x, right? The upper boundary is a line, the lower boundary is a line. When we get to the y-axis, that is when we get to x equals 0, well, now the shape changes, and the lower part of that shape is given by the curve y equals x cubed. So we'll have a separate integral here starting at x equals 0 and going up to their intersection point there. So I guess the commentary I want to have on the WebAssign problems is be prepared to solve these problems by breaking them into multiple integrals as needed. All right, so I'm going to pause the recording now for just a minute and see if folks in the live session have questions about these. Okay, guys, so I'm going to do a problem that's similar to problem 10 in WebAssign, where we have to use a couple different integrals to find our area. So what I did here, I graphed what we're gonna find here. So in the interior of these 3 lines in the parabola, there's like a upside down ice cream cone type shape, and we are going to find the area there using integrals. So the 3 equations that I used here, I have the line y equals 1 minus x. I have the line y equals 2x plus 2, and I have the parabola y equals x squared minus 1. And I'm going to try and copy this in general onto the whiteboard so I don't have to jump back and forth. Parabola is pretty easy. Whoops. If I go a little bit slower, it'd be easy. Got our parabola. We have this line going like that. And we have another line coming up like this. I'm looking for the region in between. Okay, so I'll go back to the whiteboard, I think. All right, so I just sort of sketched what we're trying to do here. I don't need to graph this accurately. I'm not trying to solve this graphically. I'm going to do it algebraically. But just to label the parts here, that's our parabola, so y equals x squared minus 1. This downward diagonal line, that is y equals 1 minus x. and then this positive slope line, that's y equals 2x plus 2. And so my strategy here, first of all, I need to notice that there's more than one function that forms the upper boundary of this region. For the first part, it's the line y equals 2x plus 2. And then those two lines cross. And then the other line, y equals 1 minus x, becomes the upper boundary. For this problem, the lower boundary is always the parabola. So I can think of this in two pieces. I'm going to set this up without the endpoints of integration, and then I'm going to put them in. I think typically when students are doing this, they often want to find the endpoints of integration first. It doesn't really matter how you do it. So I'm going to have this interval to the left, right? So from the intersection of the line of the parabola to the intersection of those two lines. So from here to here, my upper boundary is that line 2x plus 2. And my lower boundary is the parabola x squared minus 1. Okay, so that's just the left half of the graph up to this x value here. Then this other line becomes the upper boundary, and the parabola remains the lower boundary. So I'm going to pick up at some point with my upper boundary 1 minus x, and my lower boundary, again, x squared minus 1, all times dx. Okay, now these aren't yet definite integrals. I need those endpoints of integration. So I really need to find 3 different intersections. I need to find that point right there. That x value would be the beginning of my first integral. This point up here would be where I switch from this integral to that integral, so that will be the upper endpoint of the first one and the lower endpoint of the second. And then the last piece I need is this part right there. So to find the intersection of two graphs, we're just going to set their y values equal to each other and solve for x. So my first endpoint here, that's the intersection of 2x plus 2 and x squared minus 1. Okay, so if I get everything over on one side, I'd have 0 equals x squared minus 2x. I subtract 2 from both sides, minus 3. So this factors. So 0 equals x minus 3. Whoops. So x minus 3 times x plus 1. And that tells me that this parabola and that line, they actually intersect in 2 places. One negative x value and one positive x value. The one we care about is that negative value, just based on the geometry of the problem. So while they intersect at x equals 3 and x equals -1, -1 is the point that we're looking for right there. So I'm just going to label these up here. So our first x value is -1. That's where we begin our first definite integral. Then we're going to use that integral all the way up until we get the intersection of the two lines. So what's the intersection of the two lines? This one's going to be pretty easy. We have y equals 1 plus x, or sorry, 1 minus x, and we have y equals 2x plus 2. So we want to set 1 minus x equal to 2x plus 2. We'll get all our x's on one side, so add x to both sides, we get 3x. We subtract 2 from both sides, so we'd have 1 minus 2. And so then our intersection point will be -1/3. So that's the x value for this point right here. And that's where our first integral ends. Right, so it goes from -1 to -1/3. And that's where our second integral begins. So it begins at -1/3, and it'll go forward until this intersection point there. So our last piece then is to find that third intersection, and that's the intersection of the parabola y equals x squared minus 1 and the line y equals 1 minus x. Okay, so to solve this, I'll get everything on one side, x squared plus 1, subtract 1 from each side, I get -2. Sorry, that's x squared plus x minus 2. And I've set this up so these all factor. You might find somewhere you need to use quadratic formula. This is x plus 2 times x minus 1. equals 0. So really there are two intersection points, one at x equals -2. That would be like way back here. That's not the point that we want. We want the one over here. So x equals 1, right? That's our final point there. So that's the x value right there. And so our second definite interval will go from -1/3 to +1. I'm not going to go through and solve this. You guys have lots of practice doing solving definite integrals, taking antiderivatives and plugging in endpoints. The main idea in 6.6 is really in the setup of these integrals here. If you set them up correctly, you're going to get the right answer. The one thing that I know I mentioned this before is in all these subtractions here, like one function minus the other, make sure that you put that second function entirely in parentheses. Pause here again and see if people have questions about this. Okay, welcome back. I'm going to talk a little bit about some of the concepts in 8.1. These are functions of several variables. So just as a brief introduction here, we're now talking about graphs that maybe have more than two inputs to them. So our notation for these functions is going to change. We're used to f of x equals some expression involving x. Now we have functions that could have two inputs and a single output. We can think of some real-world examples of functions of multiple variables. One example that I know will show up is wind chill. So wind chill tells us how cold it feels based on the air temperature and the wind speed. And there's a formula that's used. Body mass index is another example. It uses height and weight to calculate your body mass index. So again, there are two inputs and a single output for those two variables. If we had a snapshot of the weather, for example, if we knew like the temperature at every point on Earth, we could think of a function that inputs latitude and longitude and outputs the temperature or something else about that point on the surface of the Earth. Lots of interesting functions can be made if we're able to expand beyond a single variable. So here's our notation. We'll have a function that has multiple inputs. They're separated by commas, and then we'll have some sort of formula involving those independent variables. And so I think I'm just going to talk about this one function. It's interesting, and we can analyze it using a couple basic tools. The first thing that I know you'll be asked to do in WebAssign is think about range and domain of these functions. So when we're looking at the domain of functions of a single variable, we're really looking out for a couple problems. One would be division by 0, or taking the square root of a negative number, or something like that. And so for this function of multiple variables, our domain, we're really just looking for the same problems. We just have to consider x and y. So division by 0, can we get division by 0 here? No, there's no division. There's no square roots. And so our domain here is x, right? Could be any real number. That's what that symbol means, like all real numbers. Y could be all real numbers. And this f of x comma y, that's going to have to be strictly greater than 0, right? Because if we take x and we square it, we take y and we square it, neither one of those things could be negative. And so f of x comma y, right, that's going to have to be greater than or equal to 0. So these are two aspects of the domain. And right, and here's the range of the function that tells us about the outputs. One thing that we'll do commonly is graph functions of three variables. And we'll do that by saying we have an x-axis, we have a y-axis. Let's create a z-axis in three-dimensional space, and let's use the z-axis to plot the outputs of this function. So to plot f of x comma y. So there are some conventions for graphing these functions. We typically use what's called a right-hand coordinate system. If you watch my hand here, this is my right hand. If we just had an x and a y axis plotted normally, we'd have two options for the z-axis. It could either come out of the board straight towards the camera, or it could go into the board away from you. Those would both be valid choices. In most physics contexts and in most mathematical contexts, we'll use what's called a right-hand coordinate system. And the way that we'll do that is, given an x and a y axis, I'm just going to draw those normally like we've done in the past. So here's our positive x-axis. Here's our positive y-axis. If we want to know which way the positive z-axis goes, what we'll do is take our right hand, point in the direction of the positive x-axis, curl our fingers towards the positive y-axis, and then your thumb is pointing in the positive z-axis direction. So what that means is the positive z-axis is coming out of the board. My perspective drawing is not very good here. Right, we can imagine it like coming out straight towards you, but this will be a perspective drawing. So we have x, y, and now z is coming out of the board here. So we'll label it as the positive z-axis. There are some problems where we're going to ask you to sketch some of these surfaces. You now know that I'm really not a great sketcher of graphs. Know that our expectations are not super high for how accurate these are, or we don't expect you to be incredible perspective drawers of these things. Okay, so we have some function. It's a surface, right? It's somehow a 2 or 3 dimensional surface here, and we want to figure out what this thing looks like. So we know that x and y can be any real numbers. So we would expect this to somehow expand over the xy axis, and the z values are only going to be positive. So that means that this surface is going to come out. I think someone has a unmuted mic. If you could make sure that I might be able to do it here. Hey, there we go. Everyone's muted. I did it myself. So sorry. So we can figure out what this looks like by thinking about cross sections. You guys have probably used topographic maps, maybe for navigation or for going outside, or at least you've seen them. Those have contour lines drawn on them to show changes in elevation. And our strategy for figuring out what functions of multiple variables might look like is to take a similar approach, to take cross sections of this surface and see what they look like. So for example, we're going to call this z, right? That f of x comma y, we're going to graph that on the z-axis. So what we could do is we take slices of this curve in the z direction. So slice it and figure out what those things look like. So for example, let's let z equal 0. Okay, well if z equals 0, then x squared and y squared must also both be 0, right? So that tells us that if z equals 0, x equals 0, and y equals 0, right? That's the only solution to x squared plus y squared equals 0. Not very interesting. Well, how about if z equals 1? Well, z equals x squared plus y squared, so that would mean that x squared plus y squared equals 1. And there are actually lots of solutions to that equation. You can maybe think of some, but the graph of x squared plus y squared equals 1, that's a circle. So that's a circle of radius 1. And that's what that equation gives us. Okay, well, let me pick another one here. Let me pick z equals 4. Right, so now we're taking a slice. If the whiteboard is the xy plane, I'm taking slices that are coming out along the z-axis. So if z equals 4, what's going to be true about x squared and y squared? Well, x squared plus y squared equals z, so x squared plus y squared equals 4, and 4 is 2 squared, so that's a circle of radius 2. So if you don't know that these are equations for circles, don't worry about that too much. What we're doing right now is really just exploring what the surface looks like, and there's a lot of ways that we can do that. So if we come out along the z-axis, what we're finding is that the cross sections of the surface are circles, like concentric circles. So there's just a point at the origin, and then a circle of radius 1, a circle of radius 2 a little bit farther out, and it looks like the radius of that circle is increasing as we come out along the z-axis. So taking slices in the direction of z that is parallel to the xy plane, we're getting a bunch of circles, right? You can think about what a contour or what a topo map would look like if we had circular contour lines. Like, what would that shape look like? Okay, I'm going to do one more exploration, and then we'll call this good for just an introduction to 8.1. So we just took slices in the direction of z. So we let z equal different numbers. By the way, these are called level curves here. These are level curves along z. We can also do that in other directions. So we could take slices in the direction of x, right? So slicing parallel to the yz plane. So if we let x equal, let's do x equals 1. So if x equals 1, then z equals 1 plus y squared. Okay, well, we kind of know what this looks like. If this was y equals 1 plus x squared, we know that that's a parabola in the xy plane. Well, z equals 1 plus y squared, that's also a parabola, but it's in the yz plane. So the yz plane is going to have a parabola at x equals 1. So if I come out 1 unit to here, there'll be a parabola, right, parallel to the yz plane. And if I choose other values, like if I let x equal, I don't know, 4, then we have z equals 4 squared would be 16 plus y squared. And that's a different parabola, but it's still a parabola. So what we're doing is we're starting to build a picture of what this surface looks like, f of x comma y equals x squared plus y squared. And so far we found out that there's circular cross sections in the z direction and parabola cross sections in the direction of x. So I'm going to go back to that grapher and I'll actually graph this surface and we can take a look at it and we'll call that good. Okay, so let's do, actually might need to change this 3D graph. Okay, hold on a sec here. I'll just need to reshare. Okay, so hopefully you're looking at this 3-dimensional axis system here, and it allows me to enter a function in z equals form. So I'm going to let z equal x squared plus y squared. Take a look at what that looks like. Okay, so the way that this system is set up, we have the x-axis pointing to the right on the screen, the y-axis pointing out towards us, and the positive z-axis is going up. And I'm just going to drag this around so you can see what it looks like. So here, kind of looking straight down at it, we can see where those circular cross sections would come from. I'm actually going to add some planes here. So we let z equal 0, and that just gave us a single point at the origin, right? That was where that plane intersected our surface. And we also took a look at the plane z equals 1. And especially if we look down at it, we can see that the intersection of that plane and our surface is a circle, which is exactly what we found algebraically. I'll take those away for a minute, and we can look at what those intersections in the x direction look like. So we looked at a level curve when x equals 1. So we have x equals 1. And we found algebraically that that was a parabola, and we can see that that's the case. Looking at our intersection there. And x equals 4. I'm not sure if this will be on the screen, but we can give it a try. Now that one's kind of off our screen, so we can't see where it crosses our shape here, but we can imagine that where it slices it, we'll see a parabola as well. And so this surface here, they have some cool names. This one's called a circular or elliptical paraboloid, and it has some interesting properties. Satellite dishes and telescopes use this shape. There's a point inside it called the focus, where all the rays of light or radio or whatever will bounce off this surfacing and all direct into a central point here.